Our next speaker is David Xu, who is going to introduce differentiable particles for general purpose deformed objects manipulation. David Xu is a professor of computer science and the director of Smart Systems Institute at the National University of Singapore. He's an IEEE Fellow. His research lies in the intersection of robotics and AI. In recent years, he has been working on robot planning and learning on uncertainty for human-centered robots. His work won multiple international awards, including most recently the Test of Time Award at RSS 2021. He has chaired and co-chaired several international robotics conferences and served on the editorial boards of many journals. He is currently an editor of IEEE Transactions on robotics. Please join me welcoming Professor Xu.
Microphone out for the Zoom connection?
No, it should be fine.
No, it should be fine. I'll just speak directly to this one.
Yeah.
Okay, that's good. All right, thanks a lot for having me here. Our adventure into deformable object manipulation is actually relatively recent, so I'm going to mostly talk about the student. My PhD student's work, Wei Chan, and he's going to graduate very soon. And the particular angle that we want to take it is general purpose deformable object manipulation. Explain what that means just a bit. Right, so there's a wide variety of different kind of deformable objects, and they share a set of common challenges. I'm probably belaboring the point over here, right? So they all have high dimensional state space and complex dynamics, and they want you to learn a policy. There's a limited data. Then how do we do this? I got this image from the organizer of a manipulation workshop on Monday. According to this work, word art, we should do a manipulation by imitation learning with a diffusion policy maybe implemented as a transformer. Good. How about generalization? That's good to have, but maybe dispensable. I actually think that generalization is very important. In recent years, we made so much progress in deformable object manipulation. Look at this year's workshop and also previous year's workshops, and wonderful progresses. But a lot of work focused relatively narrowly on a class of objects, sometimes instances of deformable objects, and specific tasks on those instances. For example, that if you have a manipulation system for folding t-shirts, if I replace a t-shirt by a pair of pants, my system most likely is not going to work. And if my system can do a crossfold, 50% crossfold, if I specify a small variation of the task becomes quarterfold, whether that works, that sometimes becomes a little bit tricky. And to me, that's a little bit dissatisfactory, and I'm going to explain why. Right? So this is the bedroom, probably a typical teenager, and for the graduate students over here, you don't probably look familiar to this. Right? Now, look at all the variety of different things over here. We have some towers, some drink, and maybe some straps and ropes and soft toys and all that. All these wide varieties. Now, till we try to train a specific policy for each of them. That might, to say the least, is quite tedious, just in terms of data gathering and so on and so forth. I want to ask, is it possible, can we have a unified approach to represent and manipulate deformable objects? And that is a question that we want to dabble with. But our idea is actually quite straightforward. In order to have a general purpose deformable object manipulation, we have to have a general representation first. And I wanted to propose here is a set of particles. This is a well-known idea. And you can see that the particles can represent a wide variety of different objects. Zero-dimensional objects, for example, a set of beans, and one-dimensional object is a rope, two-dimensional things like a cloth, a liquid, and liquid mixtures, and so on. Now, one of the marvelous things that happened in recent years about the particles these general purpose differentiable particle-based dynamic simulators. So there's Plastic Lab, IJCAI, our own test bench. The details aside a little bit. So all of them are general purpose particle based dynamic simulators that encodes the dynamics equations of dynamics that tells that given the current particle state and the action, what the next particle state should be, and the dynamics is parameterized by a small set of parameters phi that encodes the physical properties of the deformable object, for example, the mass, the friction, and the liquid viscosity, and so on and so forth. And there's a little bit more details of our own test bench simulator. It's fully differentiable. Differentiability is extremely very important, and we'll see just a bit. And we can represent a wide variety of different kinds of objects. And the most important of all, it is very fast. It is GPU parallelized, and we are going to use it for planning, and it must be very fast. Now, with these tools, with these powerful tools, our differentiable particle algorithm actually proceeds in two phases. The first one is differentiable model calibration. So we are going to gather a very small set of expert demonstrations as sequences of motion trajectories. And then we are going to compare the observed state with the predicted state according to the model. We compute the difference between them. The difference is measured by Schoenfeld loss between the corresponding particle states. I want to make sure to point out over here that the Schoenfeld loss basically measures the average distance between one set of points with respect to the other set of points. We do not need correspondence between the points. That is very important to keep in mind, otherwise life will be very hard. Now once we have the loss, now we're going to use the differentiability. We're going to push the gradient backwards and adjust the simulator parameters in order to minimize the loss. This is the first place where we use differentiability. Now we have a calibrated model, and then we are going to plan the motion trajectory. We're going to assume we have an initial policy. This initial policy can be learned from data through imitation learning, or if we don't do that, and then we can just use a random initialization. Then we are going to combine search and trajectory optimization together using a trajectory tree in order to plan the motion trajectory. Now, one way to think about the trajectory tree is a collection of k trajectories encoded together as a tree. Now, the first trajectory in this collection, and we have the first step, which is chosen, the action is chosen according to the initial policy, and so on and so forth, the later steps as well. So it's basically a trajectory rollout using the initial policy. The remaining k-1 trajectories are a little bit different. The first step is sampled randomly so that we have some exploration. And then, after the first step, we are going to roll out the initial trajectory. So of course, we just keep it simple. So we have only exploration for the first step. If we want, we could use multiple steps as well. So this is our set of trajectories. So this ensures that the exploration part. Now, again, we are going to use differentiability. For each of the trajectories, for any state, we compare to the goal state, again with the Schoenfeld loss, and then we're going to push the gradient backwards. Remember, there's a second place where we use differentiability. We're going to push the gradient backwards again, adjust all the actions along the way, and then minimize the loss with respect to the goal. Right? Once it is all done, we are going to choose the action at the root, at least the smallest difference with respect to the end goal state. Right? This is how we do this. And we can do this replanning at every time step and choose the best action for execution. Once the action has been executed, we can actually do one more round of adjustment of simulator parameters. This is optional in order to match up since we got the data, we can match up the dynamics more closely. Okay, so here are some results. I just want to emphasize a little more. This is a single system running on different objects. And in the lower right corner is simulation. All the other are real robotics experiments. Okay. here's a little bit more quantitative comparisons. We compared with 3 baselines. So transporter is an imitation learning policy, so it's a data-driven approach. And it's a pure data-driven approach. And CEM is cross-entropy maximization with MPC. That is a pure model-based approach. And then, of course, diffusion policy, which is very successful recently. We compared it with all of them. Right? And you can see that our method performs quite well on several tasks. One more thing we could do is actually what happens if the dynamics changes. Suppose that that we learn an imitation policy with respect to a rigid object, and if we try to apply and use our method to transfer the policy to a deformable object, would that work? Seems.
Pushes the
very important to enable us to have general purpose deformable object manipulation. When we use that one.
Sorry, David, could you turn down your audio on your laptop? You turn it up for the video, but that creates the feedback. I'm sorry.
Oh, I see. Yeah, it's great.
Thank you very much.
Thanks. Yeah, and then for this particular hanging the tower with that conclusion is not a major issue. So in general, it is. So we are looking into ways to address this issue. Now, if you think about occlusion, what's the underlying problem of occlusion? It's loss of information, right? Now, in order to address the issue of loss of information, we have to get some information somewhere else. But in particular, we are trying to train a masked encoder-decoder architecture and to learn from data to fill in the information. In particular, we use semantic information, right? And for cloth manipulation. Clothes are common household objects, and they have well-defined semantics. By taking advantage of this additional information, that we are able to predict these semantic contact points we can use for manipulation. So in particular, for generalization, the key issue I'll bring up is that it's a representation, and the representation that are able to connect perception to action. Okay. We have a poster on this earlier in the day. If you didn't get a chance to look into that and you're interested, feel free to talk to me, and also Yuhong, who is sitting over, my student Yuhong, who is sitting over there. It's all from me. Thank you.
So allowing for
to get to a question. Really awesome talk, really like this work. One of the things I'm wondering about is usually when gradients are involved, multimodality becomes an issue. Can you talk a little bit about that?
Multimodality in terms of multiple ways of achieving the same objective, or I'm getting stuck in the local minimum.
Yes, both.
Okay. I guess both issues have roughly the same answer. The challenge is that it's a very high-dimensional system, and we are trying to do research. That in general doesn't work. Therefore, I have to use the initialization. And the initialization basically ping us to a mode. And the intuition that we have is that if we use the mode in the imitation in a strict sense, therefore it gets stuck and stuck very badly. Now, what this traditionally does is to do exploration in local neighborhood, but constrained by the calibrated dynamics. That's what we are doing. It's a local search. It's not just because I have a tree or looks like a tree doesn't mean that we are doing global search. That global search in general is not no work for such a high-dimensional system.
Great, thank you.
Thank you for the talk. I have a question about the differentiable physics model. First question is, how many particles do you use to simulate?
Relatively small. 10 on the order. Of course, this is object dependent, but for the ones we are seeing over here, on the order of tens, not hundreds.
Even for the case of like a fluid powering case, really? Okay, that's interesting. So another question is about differentiable physics.
Yeah, so I want to just add an additional comment, right? So the question is, I think that our intuition of we need to have a lot of particles from the fact that we believe we need to accurately represent the state, the fluid or whatever object it is. But that's not quite true. For manipulation, what we really need is to choose the right action, not to do the right prediction of state. Of course, these two things are related, right? You can ask that if my state estimation is wrong, how can I choose the right action? But if you look at it from a different angle, from a learning perspective, what do we need? The state prediction is an intermediate result. If you are doing learning, the intermediate result may or not be exactly important. And the simplicity comes from the fact that the action choice is relatively simple.
Another question, maybe just for clarification. So for the loop of control, you simulate the environment, then you take action, then you feed back to the simulation to inform the simulation to optimize maybe the parameters. So can you give me a bit more details? What do you really simulate to optimize in this feedback loop in simulation?
Let's see, which one are you referring to? This one you are referring to?
Yeah, about here. Yeah, maybe the ones before. There is another one.
This one?
Yes, yes.
So this is the model calibration, right? This is the model calibration step.
Yeah, the model calibration, yes, that's right.
Oh, model calibration is relatively straightforward, right? So we are gathering data in the first step. So we have a pairs of x minus t minus 1 and xt, and we know the action, right? So we can simulate, we can predict the next state within a simulator.
So what is access specifically, if you can give me a bit more detail?
Oh, so in the simulator we have a particle representation, right? So we can predict the next particle state. Right. And we have an observation on x, one over here. So let me see which one is observation. Xt is the observation observed particle state, and xt hat is the predicted particle state. And these are just two sets of points, and I compute the Schindler distance between them, just by definition.
So you can only observe the surface of the object.
Okay, now I get what you're asking.
You use the Schindler distance.
Right, so now I got it. So let's talk about with respect to the liquid pouring thing. That's what you're concerned about, right? Yeah, so the liquid, I mean, that's a simulation. That, yeah, so sorry, that I should clarify a little bit more about it. The liquid pointing is in simulator, right? So we actually know the underlying particle states. That is not inferred estimated from the visual observation because it's in simulation. We know the ground truth. We know the ground truth. Right?
Okay, okay. Thank you very much. Thank you. Fine.
We're actually very good on time. Like, if there's more questions, we can have one or two more.
Yeah, maybe just a curiosity. In the videos you showed, especially with the real robot, where is the main kind of computational or, let's say, speed bottleneck that you have, and whether, like, if it's in the simulation that you do of the particles or in other parts that will make, let's say, or let's say, in other terms, what can you do to make it faster?
First of all, I'll comment about this part of what I'm showing over here. The part that's the most time-consuming part is it's proportional to the number of nodes in the tree, right? So that I need to run a forward for each node. I need to run a forward simulation, and I need to push the gradient backwards. That is the total computational cost. That's why I said that I need my desk bench to be really, really fast because it has to. It's embedded in the inner loop of traditional optimization and planning. So that is really it's just linearly proportional to the number of nodes I have in the tree. I have to push forward and push backward times. This is the main bottleneck.
And the number of nodes is the actual length of the action.
Number of nodes. No, this is the planning horizon.
So it's
how many steps I need to look ahead.
So it's time, basically.
It is time. An interesting thing is that for deformable objects, right? So it's so flexible. Try to seek long horizon planning. In the general case, that's not particularly profitable because after a few steps, you don't know what's going to happen anymore, right? That's no point.
Thank you.
Maybe I have a quick question here to clarify how many of these the first step is randomized to get different outcomes. How many of them are you normally doing? Like the K basically.
Which one?
The U2 to K.
Okay, the number of trajectories I use.
Just to get a feeling.
This one is. So I think in the 10th, sometimes hundreds.
Okay. Good. More questions? Okay, then let's thank David again.